All right, let's get started. My name is Simon, and I want to talk about Kotlin today. So I myself, I love Kotlin. I love to talk about the language, and that's why this talk is happening today. So about myself, I'm a software engineer. I live in Germany. I work there, and I've been enthusiastic about the language for around 3 years now. So I've started off as a Java developer. I used it 5 years and switched to Kotlin 3 years ago. And since then I've been teaching the language and also being kind of a pioneer for it. So I'm also kind of part of the community and stuff like that. I've also started a blog, so I write about the language sometimes, and you can find it in the bottom left corner. There's a link to it. So the agenda for today, this is all based on the latest version of Kotlin, which is 1.3.31, released last month. We're going to talk about a lot of topics, and these are infix functions, operator overloading, higher order functions, which is a very important part of the language, and also how you can inline functions. And then we're going to talk about Lambdas with receiver, which is a very unique feature of the language. And also a very big topic is DSLs. And then we're going to talk a bit about delegated properties. I had to drop generics because it's a huge topic, a very tricky topic, and doesn't really fit into this talk today, which is a shame, but yeah. So, but what I added is 2 experimental features, which is inline classes and contracts. Okay, so let's dive just right in. I'm going to sit down because I have a lot of code to show today. And the first thing I want to show you here is a very idiomatic way of defining a map in Kotlin. So what you see as a map of, this is a function of the standard library actually. And what you pass in is, you pass in keys to values. And there's a word to, and this looks like a keyword, which it isn't. It's actually a function. You can make that more obvious by adding the dot and the parentheses, which the IDE doesn't really like, as you can see. So it's suggesting to remove the dot and the parentheses. So why you can do that is because this is an infix function. And what actually happens behind the scenes, so this to function really creates pairs. So this map of takes pairs of something to something. So key value can be anything. In this case, we have string to string. So this is what infix functions look like. So this is not a keyword, it's just a function. And we can create our own function. This is actually an extension function in Kotlin. So we extend a list and we create a combine with function and we take another list. And what we do is we combine both lists. So this is a pretty naive implementation. We just combine it by adding the left and the right side and return this combined version. If we use this looks like this can be used like this. So we have one list, we combine it with another list. So we might want to do it like this. We might want to remove the dot and the parentheses. And the idea is the IDE is pretty intelligent. So it really suggests to add this infix modifier, and it just adds it here to the function. And now this syntax is valid. So a better approach of combining lists would be using the plus operator. So in Kotlin, you can't do that in Java, but in Kotlin you can use operators on pretty much every type. And we're going to look at this in the next topic. So let's quickly recap infix functions. It's a pretty easy feature actually. So infix functions let us remove the dot and the parentheses from function calls. And there are some restrictions though. So infix functions must be member functions or extension functions. So we always need exactly one receiver of this function, and we need exactly one parameter passed to that function. So you can't do that with any function. It only works if you have a receiver and a parameter. One exactly. And the most common ones are 2, as we already saw, and then there are bitwise operators like and, or, also shift operations and stuff like that. We also have some on string like zip and matches, and we have iterable stuff. So there are a few, and not too many. So this feature is not used that much, and it should be used with care. It can look a bit odd. All right, so let's move on to the next topic, which is operators. What we have here is a pretty simple data class. It wraps two integers. It's also comparable, but that's not important yet, so please ignore it. It's just a data class. It wraps 2 integers. What we can do in Kotlin is we can create operator functions. and this is a keyword. You annotate your function with it, and there's a predefined set of functions you can use as operators. Plus is one of them. In this case, we want to be able to add numeric holders to numeric holders. And what we do is we basically just add the A part and the B part together and create a new immutable object of a numeric holder. And if you provide this operator, and just to show you, I can't name it with any custom name. The compiler won't allow that because it doesn't know what plus x means. It only knows plus at this point. And if you have that, you can use this this plus operator here. This is basically what I showed in the previous example with the list. That's also enabled by an operator function. You can do that with minus as well. You can here's the minus example. You can have an increment, which allows this syntax. You can have decrement, looks like this. And this one is a bit more interesting. So in Kotlin, you can have a get operator, and this is basically what you know from array access in Java, for example. So you have the square brackets to access elements in the array. In Kotlin, you can do that with any collection type, basically. You can do that with lists and hash maps. Using the square bracket syntax, but you can go one step further and extend basically all of your types and enable this syntax. So what I did here is create the get operator, and so it takes an integer. This can also be a string or an enum, whatever, but int might make sense in this case. So if 0 is passed in, we return the left part, and if 1 is returned, we return the B part. Otherwise, we throw an exception. So now you can go ahead and grab the elements of your type by using the square brackets, and it works for 0 and 1, as you can see. Otherwise, we throw an exception. This one's also interesting. We have a contains operator. If we define a contains operator on a type, you can basically check whether the argument is part of your instance. This makes sense, for example, for sets. You can check whether some element is contained in your set. And in Kotlin, we have the in keyword to check whether this is the case. So this is often used with sets. For example, 5 in set of integer to check whether 5 is part of this set. And we can do that with any type. So in this case, we check whether 5 is part of this numeric holder, and we check whether A or B is equal to 5. This one is also pretty interesting. The invoke operator makes basically every instance of your type invocable. And if you make numeric holders invocable, you can take any instance of this numeric holder, like edit, and invoke it, as if it was a function, basically. And this is also how lambdas work in the language. So if you have a lambda in the language, it's compiled to a function, to an instance of a function type, and it provides the invoke operator. So that's why you can call the function with the parentheses. Okay, so this is another operator, compare to. It's redundant in this case because our type is already comparable. But if it wasn't, you could add the compare to. And this enables a number of operators. So everything related to arithmetic comparisons. And then we have a range 2. This also comes for free if you have a comparable, because there's an extension function, range 2. And what you can do, a range is basically, it defines a lower limit and an upper limit for your types. And you can check whether some element is part of this range. And it uses comparisons similar to these. It basically checks whether one type is bigger than the lower limit but less than the upper limit. And if we have a range, we might want to be able to iterate this range, which isn't possible by default. Whenever you have a type and you want to make it iterable in a for loop, you need to provide an iterator. And this also comes as an operator. So you can make, in this case, we need to make the closed range. You see the type here. You need to provide an iterator for this. And if you have that, you can use it in a for loop. So there's a lot of stuff you can do with operators, and I didn't cover all of them, but as we saw, there's a predefined set of operators we can use in Kotlin. You can't use everything as operators, so you can't use your custom, whatever you want. You can't use your own function types as operators, so there's a predefined set, and they all work by convention. And so we saw the arithmetic stuff like plus and minus and increment and decrement, and we also saw that the in keyword is being enabled if you provide the contains operator. Also, if you have a range 2 operator, you can use the double plus syntax. Then there's an index access if you have a set and a get operator. The invoke operator is also very interesting for DSLs. We'll see that later. And then others like compare to and iterator, and finally destructuring, which I didn't show. So this is also enabled by conventions and, for example, available for data classes by default. Moving forward, we want to have a look at higher order functions in the language. So if I talk about higher order functions, I mean functions that take other functions as arguments or return other functions. But in this case, we're just talking about the first part, so about functions that take other functions as arguments. In this case, we have a calculate function which takes a pretty simple integer first and then takes a function as its second argument. So in Kotlin, functions are first-class citizens, that you can pass them around as if you have a simple string on it. And we don't use the, so this is the syntax for functions, basically. You define that this function takes a string and then returns a string, but we can always provide type aliases to make the code more readable. So in this case, I'm not using the more verbose function syntax, but just use a readable name like int mapper. In this case, we just call the operation with the first parameter and return the value. So you need to be aware that if you use a lot of lambdas in your code, objects are being created, because otherwise they couldn't be passed around. We are still on the JVM in this case, and we need to wrap them into objects and pass them around. So if you have a lot of them, and in Kotlin you will have a lot of them, you will have a lot of heap allocations, and this will lead to runtime overhead, of course. So, but what the language provides is the inline keyword. So you can make your higher order functions inlined. What that means, it's basically a fancy word for copy-pasting. What the compiler does is, if you have an inline function, the code of the function will be copied to the places where you call that function. So the lambda is not actually being wrapped into an object and passed into the function, but the function is coming to the place where you're calling it. So there's no need to create an intermediate object anymore, and this decreases the amount of allocations on the heap. Certain situations will not allow you to use inlining. If you have, if you assign this operation to some intermediate variable like this, and you do something, and later you call that function with the intermediate variable. So if you inline this function here, you will see that the compiler doesn't like that. You can't use the operation like this, and IntelliJ says that this is an illegal usage of an inline parameter. And the thing is that it's basically the same code, but you're assigning it to an intermediate variable, and this doesn't work. And this is because so you can always use inlining if you just call the function directly, the function type parameters directly. So in this case, the operation. If you just call it, that's fine. If you pass the operation around to another inline function, that's also fine. But it's not fine to for example, assign this to an intermediate variable. And the thing is, if you assign something on the JVM, you need to wrap it into an object. Otherwise, you can't assign it to a variable. So if there's no object, it can't be assigned to some intermediate variable. And so that's why this is not working here. The IDE actually suggests to add the no inline modifier. You can see that here, and we can let the IDE do that. So you can always add the no inline keyword to particular arguments, which will mean that this function is not being inlined. Everything else will be inlined. In this case, it doesn't make sense because you only have one function that could possibly be inlined, and you're saying this one shouldn't be inlined. So this is a bit annoying, and IntelliJ again says at this point that this doesn't make sense because the expected performance impact will be insignificant. So yeah, at this point we can't do anything about it, and it couldn't be inlined. There's another situation where you should think about not inlining your functions, because if you have very long functions and you inline them, you have to be aware that this code will be appearing in a lot of spaces, in a lot of spots in your code where you call it. So because it's inlined, it's being copied to various places. So if you have long functions and you inline them, the bytecode will be much bigger than expected. Higher order functions can always be defined as extension functions as well. So you can have an extension on int and you take another function. That's totally fine. And one example of a higher order function in the standard library is the for each function. In this case, I re-implemented it. It's basically the same code, just with another name, to make it clear that this is not the standard library version. What it does, it takes an action and invokes this action on every element in your collection or your iterable. So an example of an iterable is obviously a list. If you have a list, you can call that each function and provide a lambda. This lambda basically tells the each what to do with all the elements. What we do, we check if we find an even number, and then we return from what do we return at this case? That's a question. So I have a print line here, and the question is, will this ever be printed? And I will answer that it won't be printed. So the thing is that this return here doesn't return from this function, it returns from the outer function. This is called a non-local return in Kotlin. So it's not returning from the local each, but returning from the non-local control flow. And we can fix that with labels. So what you can do, you can label your return. You can say that I want to return from each instead of from the non-local function. This is like a continue and a for loop. So it's not breaking the entire each. It's just basically skipping the current element and going forward to the next element. You can also give your custom label. That's also fine. And there's even one other alternative, which is using anonymous functions. So this is not a lambda. It's an anonymous function. It's just like a function, but without a name. And in this case, we have a fun keyword here. And if we return from that anonymous function, the return will actually return from this function and not from the outer function. And there's a simple rule to keep in mind. Return always returns from the closest function declared with the fun keyword. So in this case, return returns from this one because it's the closest fun. And looking back here, this returns from this fun. Right? So some examples of the standard library. So in Kotlin, we don't have a synchronized keyword, but we have a synchronized function which just takes the log object. And then you write your code, which is then, so this function will take care of locking and unlocking your log object. This is a good example of a higher order function, which is also inlined. Then we have use, which is like, in Java we have try with resources. In Kotlin we have that higher order function to do something on a stream or some auto-closable or closable types. And finally, what you see a lot in Kotlin is stuff like that. So this is collection operations on lists, for example. So you filter something, you map, and then you reduce. And all of these are higher order functions. So join to string isn't, but map and filter are, and they are also inline functions. And going one step further, this one is pretty interesting as well. So what we have here is an extension function, and it's called doStuff, and it's only available on lists. What we take here is another function, and this function again takes the list as its argument and doesn't return anything. What we do in the implementation is we call the provided function with our very own receiver, which is this, and this is this receiver in this case. When we call this function, so we have a list here, and we say we do stuff, and we provide a lambda, which is the argument we're expecting. At this point, what we can do, so IntelliJ says here that it refers to the list, which is the receiver, this LST here. So it really is referring to the object we're calling the function on. This is kind of redundant, right? So this basically is redundant, and I'd like to remove that. I'd like to be able to just refer to the functions and members of my type which I'm calling the function on. And this can be this can happen. And what you just need to do is put this one in front of the function. So if you do that, this syntax looks a bit like extension functions again, and you can think of it as extension functions. It's actually called lambdas with receiver. So this is a function type which has a receiver, denoted by the part in front of the dot. So the receiver of this part is the list. But in the scope of this function, you can actually use that function as if it was an extension function. And this means that you can do this dot ops. So now we can use ops as a function of list. Since this is already referring to this, and you know that you can just omit this in most situations, we could also say just ops. All of these are pretty much doing the same, and it doesn't really matter which one you choose. I'm just going to stick with this one. And now this syntax becomes so it's compilable. It compiles like this. You can also see that the list itself is now exposed as this in the Lambda. You can see that here. So now I can just say this dot size, or again omit this this part. There's actually a function in Kotlin which is called with. So you have a with function. You can put in anything like a list or string, whatever, and you this one is exposed as this in the Lambda, and you can do anything with it. Like it's called with. So yeah. Well, this was actually the right slide already. So higher order functions are a vital aspect of the language, obviously, and you see them all around Kotlin. You can always consider using inline to basically reduce the runtime overhead. It's important to be aware of this. Then there's one important thing is to remember the difference between non-local and local returns. And finally, we saw that lambdas with receiver can help us to write very comprehensive code and readable code. And this is actually a concept invented by Kotlin. So this is, I think, the only feature that is not available in any other language. And examples are with, as we saw, and also apply, which is another. They are called scope functions because you bring some object into another scope, or you basically bring your function into the scope of some object, to be more precise. All right. So the next example is DSLs. So when we talk about DSLs, domain-specific languages, what we mean is that we want to create a structure or language for setting up some domain object. So one very prominent example is the Gradle DSL. We know that Gradle can be used with Groovy, but there's also a Kotlin DSL. And this is basically, it sets up a build, and since Kotlin is type safe, you do it in a type safe way. You use that DSL type safely. Yeah, it's type safe to use it. And what I need to show this this feature of DSLs is I need a domain object, and I thought it might make sense to use a conference. Domain object, and the conference has a name and a location, and it has a schedule, which is in this case just a list of talks. And so what you can do is you can add talks, and you can get the list of talks. And then a talk can be a conference talk or a keynote talk, and a talk has obviously a topic, a speaker, and a time. So if we were to set up this domain object, we could do something like this. Any Java developer would probably do it like this. You might want to use a builder pattern for this to make it more clear what's happening there, but what you're doing is you're creating a conference, then you're creating two topics, and you're adding these topics to the conference, right? So in Kotlin, what you could do is use the apply function. If you would do conference.apply, you could just add talk without again referring to the conference object like this. This would look nicer, but we want to go one step further. What we want to have is a DSL, and a DSL in Kotlin looks like this. So I think every one of you has probably seen something like this already. It's pretty common in Groovy as well, for example. And what we have here, we have a conference block, and we set a name and a location, and then we open another block of talks. And what we do here, we have different ways of defining or adding talks to our conference. And this is just, I just added different examples to show you what's possible. So what you could do is have simple factory functions like conference talk, and you would receive all the arguments you need to set up the actual talk object. The same goes for keynote talks, and then this one is a bit more interesting. So what we have here is is basically a chain of infix calls. So we have a conference talk. We say it happens at some time, and it's given by speaker, and it's titled whatever. And finally, we have an example of an overloaded operator. In this case, it's a plus operator, and we are basically saying we plus talk, which will add the talk to the list of talks in that conference. And what we also see here is we don't have to provide a whole block of conferences. We can just add a single conference as well. And I also want to show you how this DSL looks like. So the entry point is obviously this function. This is again an inline function, and it takes another function. And this function is a lambda with receiver. So the receiver is a conference DSL, which is the most important part of this DSL, obviously. I will show that in a minute. And what we provide here is a config. So we call the conference with a config, which is this block. This is basically, you can also see here again that this refers to the conference DSL, and that's where we can just call all the functions of this DSL without any additional qualifiers like it. This is not necessary. What we do then is we create the receiver of our config, and then we apply the config, and so apply is part of the standard library again. And what we do then, so once we applied the config on our receiver, we have a fully initialized conference DSL object, and that conference DSL also exposes the properties we need to set up our conference. So we retrieve the name, the location, also the talk list, and set up our conference. So there's a lot of code which you wouldn't like to write, but if it was provided as an API, that would be not an issue. So there's a lot of code you need to write to provide the DSL, obviously, but as a user, it's nicer to use it in certain situations. So let's take a look at the conference itself. The conference DSL itself. So the conference DSL has a private backing property talk list, which is a list of talks, and it also exposes the talk list. So you can retrieve a talk list. It also has a name and a location. Both of these are vars. So in Kotlin you have var and val. So vals can't be reassigned, vars can. And this is already everything you basically need to enable this syntax. You're in the scope of conference DSL, so that means you can just access name and location, which are properties of that type, and you can reassign it to something else. That's easy. Which is a bit more sophisticated is this part, the talks. This is a property, and it's referring to another inner DSL. So we have an inner class, talk config DSL. That talk config DSL also refers to the talk list of the outer conference DSL. And it has an invoke operator. We saw that earlier. And this invoke operator again takes a lambda with receiver of its very own type, talk config DSL. And if invoked like this, it will apply the config to itself. So the invoke operator enables us to use this talks variable, which is of type talk config DSL, and provide a lambda. So because the talks is invocable, we can invoke it with a lambda. We can provide an argument to the talks. So this is the config for the talks variable, which will be applied to the DSL object. Since this is a normal reference to an object, we can just call its functions like here. So actually, the invoke is just a workaround to enable both syntaxes. Otherwise, you could always do this syntax, but we obviously want to have this syntax as well. We want to provide different talks. And that's why we added the invoke function here. So let's see how the functions in the talk config DSL look like. We have a conference talk and a keynote talk. They are, as I said, pretty simple. They just add, so they take all the arguments provided and create a talk and add it to the private list. That's all. These are more interesting. So we have, again, two properties of that talk config DSL. One is conference talk and one is keynote talk, and they basically give you an empty talk with a type. Right? So you can use that empty talk, which has a single infix function. It has an add function, and it takes a time, and it will give you a time talk. This time talk, again, comes with another infix function called by, which takes a speaker, which will give you a timed and authored talk. This timed and authored talk will finally take the topic with another infix function and add it to a talk list. That's something you don't want to implement, but it can be nice to use it because it's a pretty readable thing in the end. So it reads like a sentence, basically. So you have a conference talk at some time by a speaker, and it's titled "The Cloud." Last but not least, we have an operator. And if you define extension functions as member functions of a type, they are only available inside that type. So they don't pollute the entire workspace of the entire namespace of your workspace or your project. They can only be used in this particular DSL. And what it does is it just adds the talk itself to the talk list. That's pretty simple. And just to make it clear, I can't go ahead and use conference talk here. It doesn't know this. And it's only available in this scope, as well as this plus operator can only be used in this talks here. So you get some kind of structure by applying DSLs. All right, so DSLs, they are pretty much a design pattern for expressive APIs. And they create a structure and language for your domain objects to set it up. And they also enable a lot of code reusability. So you can obviously use your own Kotlin code inside the DSL. You can have loops inside the DSL to set up. One common example is an HTML DSL to create type-safe HTML code. And it's a combination of many language features, obviously. So we saw Lambdas with receiver, we saw infix functions, which let you provide English-like sentences or constructs. There's actually a test library for Kotlin which uses this. And you can also use member extension functions. The invoke operator is pretty common, and a lot of other features as well, of course. Okay. Let's move on to delegates. So when we talk about delegates, we mean that we want to delegate the logic for for accessing some property of your type to another helper class. And what we see here is one example of a lazy delegate. Whenever you see the by keyword, that means that we're working with delegation in Kotlin. So let's just see what we have here. We have a simple class, and we have an init block. So that means if the object is being created, it will print out something. That's all. And then we have the first example of a delegation property, of a delegated property. In this case, we have an integer and we say by lazy. Lazy is not a keyword in Kotlin, it's a function which gives you a delegate. So you always have the syntax by, which is a keyword, and then which is followed by the actual delegate. In this case, lazy, and this one takes a lambda. And in this code, you basically say what happens if this property is being accessed for the first time. And it's actually being executed only once, when it's accessed the first time. That's what lazy means. And you can even use lazy in local, so in functions as local variables. For example, if you have some code and you want to define all your variables you might need at some later point at the top of your function, you can do that. And if they mean so if they imply a heavy computation, you might not want to actually call them because you might not know if you really need them in the end. So you make them lazy. And only if they are really accessed at some point later in the code, they will be computed here. Another example of a delegate in Kotlin is the observable. So observable is pretty simple. You just provide a callback. And this callback will be invoked every time your property is being reassigned. So if this property is being changed from the outset, this callback will be invoked. You can do simple and simple stuff like just printing out what happened, so the value changed. But you can also use it to notify some other part of your system, like the UI, that you can tell it that your property has changed, please update it in the UI, which is a common use case for this. Going one step further, we have a vtuable, and this is also an observable, but it has the capability of saying, no, I don't want to assign this value to my property. So we also provide a callback here, but we return actually a Boolean. So if we return false from that Boolean, we are saying that we don't want to have this value assigned to this property. In this case, we allow all values lower than 11. So if you have a value that is greater than 10, we say no, we don't want that. So we return false, and else we just return true. Last but not least, you can obviously also have your own delegates. So you can implement your own delegate classes. In this case, we have a modifying delegate. It takes an initial value. So we are basically initializing this integer with 100. But we're also applying a modification function, so to speak. So this one takes a lambda, which does something with the value that is being passed, or that is being assigned to this integer. In the initialization, what will happen is that I used 100, and it will be multiplied with 10. So the actual value of this property will initially be 1000. This doesn't make sense, but it's just an example of how delegation works. And this is actually the implementation of the delegation class. So the modifying delegate takes an initial value, and it takes a function, the modifier. What it has here, it has a private property current, which is only the initial value applied, or the modifier applied on the initial value. So this is the initial value, actually. And whenever you call get, the current value will be returned. On the other hand, if you set a new value, which is this one, the modifier is being applied to that new value, and the current is updated. So these functions, they're hard to remember. These look a bit weird. And what you can do is, you don't have to, but you can implement interfaces provided by the Kotlin standard library. You have the choice between read-write properties and read-only properties. So in this case, we're only dealing with read-write properties. And if you implement this, you can let the IDE generate this code for you and just provide the implementation. So here's some code executing this, using this delegation stuff. So what we do here is we access lazy one twice, and what we're expecting is that the initialization of this lazy one, so this is basically the name of the property which we use with the lazy delegate. At this point, you only see that lazy in it once, because and you can also see that it's not invoked directly, but only after we created the object and called the lazy one property here. And it's not happening a second time. If we assign observed property, we see that the value has changed. We're setting verified property to 6, which is fine, no veto. Setting it to 6 is not fine, veto. And if we then print the current value of verified property, it's still 6, so 11 has not been applied. Finally, the custom delegate, we set it to 2, and the value then is 20, because we multiplied with 10 in the modifying delegate. Right, so delegated properties let us reuse property accessor logic, and this is always denoted by the by keyword. We also have class, I'm not sure if it's called class delegation, but you can actually also delegate to implementation. So if you implement an interface in Kotlin, you can delegate that to a class. So you can, for example, have your own map and delegate the map implementation to an internal map or to a private property which you have in your class. But this is a bit different, but still also uses the by keyword. The compiler will generate all the accessor logic for you. So if you have the by keyword in your code, it will actually in the bytecode have another property referring to that delegate, and whenever the actual property is being used, it will delegate to that property using the set value and the get value functions. Right, so this feature is sometimes used will sometimes be used in your code, but it's also very often used in framework and library code. So there's one example, which is the exposed library, which is it's an SQL generation library written by JetBrains, and they use it a lot to basically abstract the access to table fields in SQL. Right, so the next topic is inline classes. And as I mentioned earlier, this is an experimental feature. So Kotlin introduced this kind of experimental features to say that this might change in future releases. So what all that I'm going to show next is the current state of the language, but it might change in future releases. So inline classes. If we have a simple API method authenticated, it takes two strings in this case. It takes a user and a password, and you can use it basically in two ways. You can use it in the correct way, applying the username and the password, or you can confuse the order of the properties, which is not very it might not happen in this case, but if you have a lot of booleans or strings, this might happen. You're going to confuse the order of the properties, and this is happening because they are all of the same type, which is string here. So this doesn't give you a compile time error, but it will fail at runtime. What we can always do is wrap simple types like strings and integers in another wrapper type, and you can use classes for this. But in Kotlin, you can also use inline classes. And the cool thing about inline classes is that if you have an inline class, this will not lead to actual object allocations. So if you have a string and you wrap it in an inline class, you won't have that name object in the bytecode. This is not entirely true. It might happen. There's something going on like boxing, which you know from the integer type in Java. But the compiler will try not to use this class in the bytecode. So it will optimize it by just using the wrap type or the underlying type, as how it's called. So what we can do is we can wrap the name and the password, and we can think of this as subtyping the string. And we are using these types in the authenticate method then. And what we have then, we can't confuse the order anymore because the compiler will tell us that this is not valid. We can't just change the password and the name. So it gives us more type safety. Another example that might make sense here is something like this. So we have a function that takes a number, which is a string, and it passes this into a big decimal by setting a scale. So it's basically not taking the entire string but part of it, and setting the scale and also rounding with the half up technique here. So we have that, and it might happen that the requirements change, and we might want to preserve the original value, which is the string. So if you have something, you pass it, and you also want to preserve the original, it might make sense to just create a class and provide that functionality. That makes sense. But if you use it, if you use these types a lot, these will mean a lot of heap allocations. Then again, it might make sense to consider inline classes here. So this inline class wraps the original string, and inline classes can have functionality in their body. So they can also have properties, which must be calculated properties. So whenever this passed value is accessed, the get method will be called, and it will actually do the calculation. So this is not cacheable in this case. It has to happen every time. This is we can say it's a downside. So the trade-off that it needs more calculation at runtime. But the cool thing is that you can now use the parsable number with these two properties. And as an API user, this looks like they are just simple properties. It's important to again note that at compile time, this parsable number won't exist. And this parsed here is being enabled via static functions. So there will be something like a parsed function. It will take the original string and then return the big decimal. Pretty much like this one, but we're still preserving the original. Yeah, so again, it's an experimental feature. It might change, but it lets us wrap types without runtime overhead, and it can be used for simple types, to wrap simple types. And as I said, normal classes, of course, imply heap allocation, so that's why we might want to use inline classes instead. And it's important that if you have a name class which wraps a string, and you have a string on the other hand, you can't just assign them to each other. They are not assignment compatible. On the other hand, type alias, which I showed earlier, is assignment compatible. And inline classes only work if you have a single property defined in the primary constructor. So this is the underlying type of this inline class. But we can have functions in the class, and we can also have member properties. Last but not least, I want to talk about contracts in Kotlin. So consider this code. We're having a function here which takes a nullable version of a list of strings. So as you know already, probably the question mark denotes that this is nullable. So it might happen that this is null. And what we do here, we check that it's not null and it's not empty. And in the next line, what we want to do, we want to print the size. And the compiler doesn't like that. It's telling us basically that it can be sure that data really is not null at this point. But we checked it here, right? So we are expecting, because the Kotlin compiler is pretty smart and it can normally do these kinds of things, but in this case it can't. And the reason is that this is a function here. So it's null or empty is a function, and the compiler doesn't know what the function actually does. So does it really check that the type is not null? If we have a look at the implementation, it does check it. So it checks that. So it returns. It checks whether this is null or this is empty, and we're checking that this is not the case. So we are checking not is null or empty. So what we can do in Kotlin since version 1.3, we can add a contract here, which is also DSL, and this looks like this. We still have to opt into I'm confused. Okay, here we go. So we have to add an annotation and say that we're using the experimental feature of contracts. This is a bit noisy and it's not nice, but it's the current state. And what we have here, we say that the contract, if it returns false, this implies that this is not null. And we're basically telling the compiler a bit about the function we're actually having here. And now this code is fine. And it actually says that a smart cast happened to the non-nullable version of a list. There's another example where contracts make sense. If you have a value and you assign this value later, this is fine. So values can be assigned once. They must be assigned exactly once. And if you have a function, or you delegate the initialization of that property to a function like here, to let, the compiler doesn't like that because it might do, so the let might call this function you provide multiple times, and this would mean that the property or the variable would be assigned multiple times. So it doesn't allow that. Again, we can use contracts to solve that, and what we do then is we say that if this function is called, it's being invoked exactly once. So we tell the compiler that this function will only call block once. That means that this assignment will only happen once. So that's what we can do with contracts. Also experimental feature, but they let us help the compiler understand our code. So smartcasts are always based on perform checks, like if something is not null, and then the smartcast will happen. But this is problematic if the checks happen in a separate function. And the contracts let us describe how functions behave. And one thing to remember is that these contracts are not checked by the compiler. So whatever you say in the contract, the compiler will believe you. So it's your responsibility to make sense of this feature. Yeah, so a little summary. This is really simple. So as we saw, Kotlin has a lot of features, and they might look magical at first, but I think it's very important to know how they work internally. So I always say you should read the documentations, which are pretty good. And the best book out there is Kotlin in Action. So if you haven't read it, please grab a copy and read it. It's based on Java developers, and it tells you a lot about the internals and how how the language is implemented. So the authors are actually they're involved in the language. They work for JetBrains, and they know what they are talking about. So that's it. Thank you very much. You can find the code there if you like on GitHub. And yeah, thanks. So we actually have 1 minute, so one question would probably work. Otherwise, I'm around, so you can just come to me afterwards.